right, senior math. Today we are jumping into something new. We are going to talk about probability. So, what is probability? Probability is calculating, where it's the math of, sorry about that. It's the math of calculating the likelihood of an event. And that event can be anything. That event can be rolling a dice. It could be winning the lottery. It could be getting struck by lightning. It could be whatever. We can, as long as we have information about that event, we can calculate the probability using probability. So how do we determine the probability of event? So what do we look for when we're determining the probability of event? So probability is always, so the probability of an event, this is going to be math notation. So whenever we're trying to calculate the probability of something, whenever we're writing the probability of that event, we write P with parentheses, and then whatever the event is inside. So let's see the event A, whatever event A is. P, the probability of event A is equal to, an event A could be rolling a dice, flipping a coin and having it land on heads, finding a $20 bill down the hallway. I don't know. So the probability of event A is equal to the number of desired outcomes divided by the number of total outcomes. So what this means is the number of outcomes that you want to happen for event A to occur divided by the total possibility of outcomes that can happen. So for example, if you roll a dice and you're trying to get a 1 on that dice, you have one desired outcome, rolling a 1, out of 6 total outcomes on that 6-sided dice. Or if you're trying to get an even number, I have 3 potential even numbers that could show up on that dice. So I have 3 desired outcomes out of 6 total outcomes on my 6-sided dice. So probability is always the number of desired outcomes divided by number of total outcomes. It's also always going to be a number between 0 and 1. We can never get a probability less than 0. We can never get a probability greater than 1. It's always going to be in between. Where 1 is absolutely certain. It's 100% going to happen. 0 is impossible. It's 0% going to happen. While 0.5 or 50% is going to be equally likely to occur or equally not likely not to occur. It's 50-50 chance. When you're greater than 50, you're in that more likely region. When you're less than 0.5, you're in that less likely region. So it's always going to be 0 to 1 or 0 to 100 if you're thinking about percentages. Probability will always be within that range. Typically, as mathematicians, we just leave it as a decimal, but if you like to turn it into a percentage, if that's easier for you, then that's fine. You just have to multiply your decimal by 100. All right, so a quality control inspector samples 500 computer monitors and finds defects in 3 of them. What is experimental probability that what is the experimental probability that a randomly selected computer will have a defect? So experimental probability, we're talking about 2 probabilities today. We're talking about theoretical probability and experimental probability. Experimental probability is probability based off observations, based off actually seeing things and testing things. So what information were we given? So quality control inspector sampled 500 computers. So there was 500 total computers, and 3 of them had defects. So our experimental probability, our probability of getting a defect in a computer is 3 out of 500. Our desired outcome is the defect out of 500 total outcomes. So 3 out of 500, all we have to do is turn that into a decimal. So 3 divided by 500, and we get 0.006. So that is our probability of getting a defect, our experimental probability. We're using the information given to us. We're using the observations that were given to us. So once again, this is very, very unlikely to find a defect because it's very, very small. It's very close to 0. Now, let's say if the company manufactures 15,240 monitors in a month, how many of those are likely to have a defect? Well, if we're trying to figure out a likelihood, if we're trying to predict with probability, all we have to do is use our experimental probability and multiply by the number of occurrences. So we're going to take our experimental probability of 0.006, and we are going to multiply that by our total number of computers that we're going to be testing, which is 15,240. So we multiply these together. This is going to take our potential of finding a defect times the number of potential computers, and that should tell us how many computers there are that should have a defect. So that is 91.44. So roughly about 91 computers or 91 monitors, whatever, should have a defect. Once again, this is an experimental probability. It's based off of our experiment. So we might test through all those computers, and it's possible that maybe none of them have any defects. It's possible. We might test through all of those computers, and it's very, very unlikely, but it's possible that maybe all of them could have defects. So with probability, there's always a chance for things to occur. This is just our estimation or our prediction based off probability. This is what should happen. Doesn't mean it always will happen. It's kind of like if you ever seen the movie Dumb and Dumber, when there's the one guy asks the girl out and he's like, not in a million years, or oh, never mind. I forget the quote. Okay, ask me later. I'll remember it. All right, so a park has 538 trees. You choose 40 at random and determine that 25 are maple trees. What is the tree chosen at random is maple? So once again, we're using experimental probability. So it's always based off. So if we're looking for the probability of a maple tree, it's our number of desired outcomes divided by our number of total outcomes. So what is our desired outcomes? Finding a maple tree. We found 25 of them. So 25 out of how many total trees did we test? 40. We chose 40 at random. So 25 out of 40 is our experimental probability, our desired outcomes versus our total outcomes. Out of the 40 total trees we tested, 25 turned out to be maple. If we divide that, we get 0.625. So about how many trees in the entire park are going to be maple? So we know there's 538 trees in the entire park. So if we want to find the experimental probability, or if we want to find out roughly how many trees in the entire park are maple, we're just going to take our experimental probability of 0.625, and we are going to multiply that by 538. Take our total number of trees times that experimental probability. And we get 336.25. So roughly, once again, 336 trees should be maple. Doesn't necessarily mean that they will be, but 336 should be based off that. So that is experimental probability. You did an observation, you have some data, you're using that to predict the future events. So the other type of probability is theoretical probability. So probability is based off of what we know about the event without performing any tests. So this is based off what we know should happen, but we haven't done anything yet. So experimental or theoretical probability could be like rolling a dice and flipping a coin. We know what should happen. We know the odds of those events, but we don't necessarily know what is the actual occurrence is going to be. We haven't done any tests. I haven't rolled 36 dice yet to figure out what my experimental probability is. I just know that based off of dice having 6 sides, I should have a 1 in 6 chance of getting whatever number. So what is the theoretical probability of drawing a queen from a deck of cards? All right, so we have to use our knowledge of our deck of cards to figure this out. So I know that my probability of getting a queen is my desired outcome divided by my total number of outcomes. Well, how many queens are there in a deck? How many desired outcomes do we have? So if we think about a deck of cards, we have 4 queens, 1 of each suit. And then if we think about the total number of outcomes, how many total cards can I draw from a deck? Well, there's 52 total possible cards. So I have a 4 out of 52 chance of getting a queen. 4 out of 52 is 0.07, we'll say 0.077. So that is our probability of drawing a queen from a deck of cards. 4 out of 52 chance. These are 4 possible queens out of 52 total cards. And once again, we didn't do any tests. We didn't draw a bunch of cards from a deck testing this experimental probability. All we did was we used it based off of our knowledge of what is in a deck of cards without having to test anything. So that's theoretical. So what is the probability that when we're rolling 2 standard dices adding the total is 7. So when you roll 2 dice like you're playing Monopoly or something, what's the probability of getting the number 7 by adding those two numbers together? So with this one, it's a little bit trickier because there's a lot of different combinations that could come up. Because you could roll a 7 with a 1 and a 2 and a 5, with a 3 and a 4, with a those probably about it. I'm definitely missing some. But in order to calculate this, there's lots of different ways that we could roll 7 on 2 6-sided dice. Because it could be, I could get a 6 on one and a 1 on the other, or a 1 on one and a 6 on the other. So there's lots of different chances. So what we're going to do is we're going to make a little table. Gosh dang it. Let me plug in my computer really quick. I apologize for this. So we're going to make a little table. And on this table, we're going to split it up into 6 different regions. And these 6 different regions are going to help us determine what is the total number of outcomes versus how many total numbers are going to be 7. When you start using multiple dice at a time, this is helpful to us. Doing like a table like this, it's helpful to see what are all the possible outcomes versus the total number of outcomes. So I'm going to split this up into 6 regions. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. So on my first dice, it's possible I could get a 1, a 2, a 3, a 4, a 5, or a 6. On my second dice, I have the possibility of getting a 1, a 2, a 3, a 4, a 5, or a 6. Now all we have to do is tally up these totals and figure out which of them are 7s. So I have this 1 plus 1 is 2, 1 plus 2 is 3, 4, 5, 6, 7. That's a 7. So we'll make that in blue. 2 plus 1 is 3, 2 plus 2 is 4, 5, 6, 7, 8. 2 plus 1 is 4, 5, 6, 7, 8, 9. 1 plus 4 is 5, 6, 7, 8, 9, 10. 1 plus 5 is 6, 7, 8, 9, 10, 11. And then 6 plus 1 is 7, 8, 9, 10, 11, 12. So those are all the possible combinations we can get on a 6-sided dice using that table. So if we look, there's 36 total possible combinations. And out of that 36, only 1, 2, 3, 4, 5, 6 of them are 7. So our probability of getting a 7 on a 2 6-sided dice is 6 out of 36. Which if we divide that, 6 divided by 36 gives us 0.167. So roughly about 17% of a chance we're going to get a 7 on a 6-sided dice. Now, if we look, 7 is the most common number we can roll, but there's lots of other numbers that can also show up on those 2d6. So what is the probability of getting a 9 on a 6-sided dice? Well, once again, all we have to do is look for how many 9s do we have. So I have a 1, 2, 3, 4 9s. So we know the probability of getting a 9 on a 6-sided dice would just be 4 out of 36. And then we can figure out what that decimal is. Or the probability of getting a 13. Well, okay, let's look at this one. Probability of getting a 13. How many 13s do I have on here? Well, the largest number I can get is 12 because they're both 6-sided dice. So my probability of getting a 13 is impossible. So it's 0 desired outcomes out of 36 total outcomes. So it's 0. It's impossible. There's no chance that I can get a 13 on a 2 6-sided dice because it will never happen. So it's a 0% chance. And then we can do 4 divided by 36 for that chance. So when you're having multiple dice rolling and you're trying to figure out what are the total possibilities, make a table like this. It's very helpful where you're adding the totals together. All right, what is the theoretical probability of rolling a number greater than 4 on a standard dice? Okay, greater than 4 on a standard dice. So we think about our standard dice has 6 sides. So if we're trying to find the probability of rolling a number that is greater than 4. So what numbers are greater than 4? Well, 5 is greater than 4, 6 is greater than 4. So we have 2 numbers on our 6-sided dice out of 6 options that could be greater than 4. So 2 out of 6 is like 0.33 repeating. So that's our probability of getting a number greater than 4. So let's say that was the theoretical probability, right? So let's say I rolled a dice 12 times and got these results. What is the experimental probability of getting a number greater than 4? So theoretical is what should happen. Experimental probability is what did happen. So based off our experimental probability, how many times did I roll a number greater than 4? Well, these are our two numbers that are greater than 4. So there's a total of 5 times out of 12. So our experimental probability of getting a number greater than 4 was 5 out of 12. Well, let's see how does that match up to our theoretical probability. So that's 0.417. So there's pretty much we had a larger chance apparently. We got more numbers greater than 4 than what were initially expected. We were supposed to get around a third of our numbers were supposed to be greater than 4. We got roughly about a quarter, or roughly about 41% of our numbers were greater than 4. So once again, experimental probability won't always match up to your theoretical probability. This is what should happen, but this is what actually happens. All right, one last thing to talk about today. So this is called the complement. The complement of an event consists of all of the outcomes in which the event does not happen. So if we're looking at what is the complement of rolling a 1 on a standard-sided dice, it's all of the events that you don't roll 1, which would be rolling a 2, rolling a 3, rolling a 4, rolling a 5. Those are all the or rolling a 6. Those are all the complements of the event. So anything in which it does not happen. So the way we calculate a complement of an event is we typically, when you're trying to find the complement of event A, typically we put this little C next to it. So this is saying you're trying to calculate the probability of a complement of event A. Or sorry, typically we put it on the inside of parentheses. So the complement of event A is all the times where event A doesn't happen. And the way we calculate this is you take 1 minus the probability of event A. The reason we calculate it this way is because probability of event A has a certain percentage. If we take 1 minus that percentage, that's going to give us all of the other percentages in which A does not happen. So that's how we calculate the complement, is you just take 1 minus the probability of the event. So what is the probability of rolling a number less than 3 on a standard-sided dice? So we're trying to figure out what is the probability of rolling a number less than 3 on a standard-sided dice. Well, what numbers are less than 3? 1 is less than 3, 2 is less than 3. So that's once again 2 out of 6 chance of getting a number less than 3, which we know already was 0.33. So if I want to figure out what is the complement of this event, if I'm trying to find what is the probability of rolling a number less than 3 but I'm finding the complement of that event, all the chances where that doesn't happen, all I need to take is 1 minus 0.33. I just take 1 minus my value, which is going to give me 0.67. So anytime we're trying to find the complement, all you have to do is take 1 minus. Now it's very possible we can always calculate the probability of rolling a number less than 3, the complement of that event, just by calculating. I know what numbers are less than 3. Well, 3, 4, 5, and 6 are all numbers that are not less than 3. So I could do 4 out of 6, and that will give me that same probability. So I can still calculate it the normal way. But if you already have the probability of the original event, finding the complement is very easy by just doing 1 minus that probability. All right, last thing is where we'll end it for today. So a jar contains 10 red marbles, 8 green marbles, 5 blue marbles, and 6 white marbles. What is the probability that a randomly selected marble is not green? So I'm looking for a randomly selected marble is not green. So essentially, I'm looking for the probability of the complement of green, which I know is going to be 1 minus the probability of getting a green marble. So, well, what is my probability of getting a green marble? Well, the probability of getting a green marble is going to be our total number of green marbles, which is 8, out of our total number of marbles. So I have 10 red, 8 green, 5 blue, and 6 white. So that's 10 plus 8 is 18, plus 5 is 23, plus 6 is 29. So 8 out of 29 marbles should give me 0.2. Our 0.275, I'm going to round that up to 0.28. We'll go to 2 decimal places. So I know the complement, the probability of getting a not green marble is going to be 1 minus 0.28. 1 minus 0.28 gives me 0.72. Now, once again, it's possible that you could have calculated this by calculating all of your by adding up all your total number of marbles that are not green, which would be 10 plus 5 plus 6, which would be 21. And you could do 21 out of 28, and that will get you the same answer as this. Or you can calculate what is the probability of getting a green and then doing 1 minus that probability. So what's the probability that a randomly selected marble is not red? So once again, we can calculate this by doing probability of getting a red and then doing 1 minus that probability. So the probability of getting a red marble is 10 out of 29. We knew there were 10 red marbles out of 29 total. So 10 divided by 29 is 0.34. So our probability of getting not red, the complement of red, is going to equal 1 minus 0.34, which is going to give us 0.66. So about roughly 2/3 of a chance of getting a probability of not green. Or not red, I'm sorry. So that's our probability. You're going to have a chance to practice theoretical and experimental probability for a little bit after you did that Desmos activity. Let me know if you have any questions over this. We'll be doing probability for about 2 to 3 weeks from now. Yeah, have a great rest of your day.